simulation. Last time it was not quite shown yet. I suggested a small simulation, and one student was interested in doing that, but now I don't see him anymore. We wait maybe until I return. So.
No,
or he will not return.
I think I will not return.
Ah, okay. We should think about it. Okay. Okay, so are you ready? Good. So, okay, this is again the plan for the 4 lectures, and last time we have basically introduced quantum mechanics in terms of half integrals. In particular, we proceeded already to the Euclidean space and established a link to statistical mechanics in the terminology of partition function, expectation values, and we got basically to this line the treatment with Monte Carlo simulations and how one could basically evaluate, for instance, the energy spectrum of an harmonic oscillator even at finite lambda, at finite interaction or coupling. So now we are at this point. We will discuss spin models in statistical mechanics, and in some sense we repeat what we did before. We will see something very similar, but at the same time we prepare, this is the final preparation then to get to quantum field theory in the lattice regularization, which has a very smooth continuation. It is basically putting quantum mechanics, regularized quantum mechanics and statistical mechanics together, then we get quantum field theory in the functional integral formulation, and then we will start, of course, with the simplest case with a scalar field, and here we can do some explicit calculation to see that the formulation works. There are a few things that one can compute explicitly, and then the continuation will be to introduce other types of fields, both gauge bosons, fermions. Then we will have the full lattice QCD, that this is then for next time. So we are, okay, maybe here we have done this part, classical mechanics, quantum mechanics also, and now we are in the transition to get to the right hand side to field theory. So this is what we did before. This is what we also did. Okay, so here we are now. This we haven't done yet. So in some sense we start from 0, but we repeat things that we did before in a different language, and we are anticipating quantum field theory, which is supposed to follow, and we will do the transitions between different branches of physics. I will show you some dictionaries how to translate the terms from one language into the other. So first of all, we are now going to deal with an object that we call classical spins. A classical spin, the simplest form can be simply a real vector with n components, or it can also be complex. It is not a quantized angular momentum. This sense spin should maybe be written in inverted commas, but this is how it is done in the literature. It is much simpler than that. And quantum spin models also exist, but they are much more complicated, and we will not really discuss them. The simple spin models have actually more applications in the real world. So what we do is we take a set of discrete points, space points that we call X. For instance, they can be on a cubic lattice, so separated by a spacing that I call A. So in each direction we have a point and each multiple integer of A, and on each such a side, lattice side, we attach a spin vector of n components. Then it is very useful or often done that we say all these spins on each side X have the same length, and if they have the same length we can normalize this length to 1, and this is what defines the most popular spin models. And now we can distinguish how many components n there are. So we have two spaces here. The dimension of space, x, this can be 1, 2, 3, whatever we are interested in. And then we have the dimension of the spin space, n. They are basically independent from each other. Now if we have this constraint, and the simplest case would be n equal 1, then each spin has only two possible orientations, plus or minus 1. This is called the Ising model. Seems very simple, and people thought for some time it is too simple to be a useful model, but actually it turns out to be the most successful model of statistical mechanics that exists. Why this simple model can be so successful, we will comment on that later. Let's say if we take two components, or two or more components, then these spins can be rotated with an ON group, so that's why they are called an ON model. And if we write the Hamilton function properly, the system has this symmetry, has an ON global symmetry. So we can then look at n equal 2, so then this is rotation in a circle. We can, this is called the XY model. Actually the notation is not so good because XY suggests that, we parameterize the axis on the spin space as xy, so this is a bit confusing. This is not, okay, this is the name. It simply means that we have two components of this vector, and this applies very well to superfluids, which have exactly this symmetry. People also apply it to superconductors, but there it's a bit less direct because there is an O2 symmetry, but a local one, not a global one. So the most direct application here are superfluids. And then n equals 3 is called the Heisenberg model. This describes obviously ferromagnets, where spins can rotate in space. n equal 4 I did not write here, but it also has some special meaning because of the local isomorphy to SU2 cross SU2, right? There's some local isomorphy, and as you know, if we deal with fermions, this can be left and right-handed chiral symmetry. So O4. So O4 also has a special interpretation, in particular in chiral perturbation theory, which we will discuss next week. And then also there is a lot of literature about n very large. So if we take the limit n to infinity, the models simplify mathematically and one can solve certain things that one cannot do otherwise. And then people add a 1 over n expansion and compute maybe a 1 over n and 1 over n square correction to it. And if one is lucky, one can then relate it to the small n's 1, 2, 3, 4, which are of interest. So this is a mathematical trick. It's called the spherical model. Now, what is the physical motivation? The spatial lattice can be a crystal of a solid state, and then S would be a collective variable. We have a set of a lot of electrons in each such cell, and if we put them together, the collective spin can well appear like a classical spin, where the quantum structure of the spin is not visible anymore. So in solid state physics, this actually is quite applicable, and there is a difference with the discretization that we had in time before we regularized time, or Euclidean time as a mathematical trick, as a regularization. Here we can say if we really deal with a crystal in solid state physics, then it's not a trick, then the structure is really there. However, we can also interpret it as an interpretation and take a continuum limit. This is what we will do later in field theory. And to complete the model, we have then to define something. Let's say we define the energy as a function of these spin orientations. If we take if each spin chooses its orientation, we call this one configuration. So each, let's say, if it's a Heisenberg model, each spin chooses if it wants to be up or down. If this is all fixed and each x, then this is one configuration. And we can assign to each configuration then the energy that the model requests, and this is what we call the Hamilton function. It's not the Hamilton operator, it's just a function of the configuration. And the Ising model usually would be done like this. We sum, this symbol means the nearest neighbor sides. So the product of the nearest neighbor sides with some coupling that we can call J, and then maybe some extra term which corresponds to an external magnetic field. So first about this J. Let's say if J is positive, the energy will decrease if the nearest neighbors are have the same sign, right? Same sign, both positive or both negative. This will decrease it, so this is favored because the system always looks for energy, for lower energy. So that means the system is ferromagnetic. Or if we take J negative, then it's the other way around. It's an anti-ferromagnet, and the spins prefer to be up, down, in a checkerboard style. So that would then be, let's say without this term, that would be the ground state of the system. So this favors a parallel or an anti-parallel orientation of the nearest neighbors. So in this case, at least finding the ground state is very simple, as we see. If we just, what we mentioned before, these quantum spin models, in this case, actually even finding the ground state is very difficult already. So we see they are really much more tedious to deal with. And then we can add such a term here, say with a constant h, which is like an external magnetic field. And if the spins have the same sign as this h, then the energy will be lowered again. So this justifies the term magnetic field. Or we can we could also make it more sophisticated and say this h could also depend on the side. So then it is what we would call a source in quantum field theory. We will come back to that. But this is the extra term that we could easily add.
Wolfgang.
Yes.
Can I adjust the brightness of your computer? Because I think
it's something. Sure.
There has been some decrease in brightness.
Yeah, we did some manipulations yesterday to connect it to the cable. It's a bit darker than last time.
Não, estava.
Hein? Eu tinha encontrado, mas não está fazendo efeito nenhum. Alguma coisa.
Fonte externa.
Será que desconectou?
Só se a fonte caiu. Está na bateria.
No, actually, it's disconnected.
No contact.
Maybe this. Is there a power supply from there or maybe I can use it?
This has to be connected. Oh, this one.
I also
can use this one. Let's
see if it's possible.
So. Então, melhorou?
It's better, yeah. So probably the other one doesn't have. Yes, I think it's better, right? Okay, thank you very much. Okay, now once we have defined the energy for each configuration, we are back with what we did last time, introduce the partition function, which means we sum over all possible configurations. For the Ising model, this means a product over each point, and in each point the sum over the two spin orientations, plus minus. And if we do this sum, this I write symbolically in the same language as last time, as a functional integral over all configurations, and each configuration has this exponential factor minus energy divided by some temperature. So this will stay with this symbol, which means in general the sum over all configurations. If n is larger than 1, we are not only with an Ising model, then we would have a product here over the spin components, and each component an integral from -1 to 1, and then we have to fix the norm of the spins with such a delta function. And again, we see here that the ground state, the minimal state, then has the lowest energy, makes the largest contribution to the partition function, and this can be a ferromagnet for a ferromagnet that all spins are parallel, for an anti-ferromagnet that they are staggered up, down, and the rest is somehow exponentially suppressed. How strongly it is suppressed depends on the temperature. For temperature 0, the suppression is total, is complete. For larger temperature, the higher the configurations with higher energy also contribute more and more. This all makes sense intuitively also. And now we can measure, as we have seen last time, also expectation values. The simplest expectation value would be magnetization. We can call it a one-point function, where we insert here a variable at some point x, and then take this sum and normalize over the partition function, which does not have this extra factor. So that would be the expectation value of one of the spins. And actually, since we sum over all configurations, it doesn't even matter which side x we take, so it is enough to write this as an expectation value of the spin itself. Not it will be the same for each side. And then what is usually more interesting is again this correlation function that we plug in here two spins at general at different sides that I call x and y here. Again we normalize here and the rest is the same. And typically we want to know how strongly the spins affect each other. So if we have one at x with say orientation up for an Ising model, its neighbor has a strong trend to be also up, but if you go a larger distance away, then this trend shrinks away and it is getting more and more decorrelated, and we want to know how strongly they affect each other, how strong the trend is, say for a ferromagnetic system, to have the spins parallel as a function of the distance between x and y. Now if we do that, this is we refine the definition a little bit. This is what we called connected correlation function last time. We subtract the term that as if the x and y were completely independent. This term contributes also, but in the correlation we really want to know how they are correlated, how they affect each other. So we subtract the term that would be a completely independent expectation value at x and y, and what is left in this difference is then what we call the connected correlation function. This describes really how they affect each other, and in most systems it is a very general rule that this decays exponentially with the distance. And this exponential decay must of course have a coefficient here, we can write it as an inverse coefficient, which must have dimension length, and because the exponent is dimensionless, and this is known as the correlation length. The correlation length is the most natural scale of a system. So if some being lives in this system, it will take the correlation length as the scale to compare it to anything. If everything is large or small, he will always decide by comparing it to the correlation length or some power of the correlation length as the most natural intrinsic scale. We have already mentioned that it corresponds in quantum mechanics or in field theory to the inverse energy gap and also to the inverse particle mass. But for the moment I call it the correlation length of the system. And intuitively you can say if the temperature is high, then a lot of wild fluctuations contribute significantly to the system, then the correlation cannot be very long. So then this will decay over about 2-3 Lattice spacings. This will decay very rapidly, and psi must be very short. And we have seen also last time, okay, we have a continuum limit. If psi can become very long, it can in principle diverge. And maybe in the first reaction would be, well, this happens if the temperature goes to 0. And this can be the case, but it doesn't need to be always the case. It can also be at finite temperature. That's we will discuss in a moment. So first question is, we say we limit the interaction of such spins to nearest neighbors. Is this actually a reasonable approximation or not? If we have spins in a solid, you can say, of course, they affect the nearest neighbors most strongly, but then there will be a smaller interaction to the next nearest neighbor and so on. So actually it is more complicated. Is this a good approximation? And the answer is yes, it is very well, it can very well be a good approximation, because if at some temperature, which I call a critical temperature, psi goes to infinity, then all these details, how the couplings are spread over the neighbors, nearest and next to neighbors, do not matter anymore, because one lattice spacing is then negligible compared to to the correlation length, and in the vicinity of such a second order phase transition where psi goes to infinity, the details how we put the couplings within a short range do not matter. And that is a very important property. If we would not have this property, we would have a complete mess. For every variant of the model, we would have new physics and we don't know which is the correct one. So thanks to this property, which we call universality, we know that all these variants of the models where we add a little bit of couplings to other spins and so on, ultimately near the second order phase transition, they will give the same results because these differences, the short range differences, do not matter anymore once psi is very large, much larger than a lattice spacing. The term second order phase transition is because it is based on a second derivative of the free energy, also of the partition function, if you wish. So this second derivative can be seen if we have such an external source here, and okay, let's say we take it as h and take two derivatives of this h, then we get this x, this is what we have seen last time, then we get this sx, xy here. So we take two derivatives of the fundament of the root system. So that's why the term second order comes about. And this property is very characteristic for second order phase transitions. Actually, second order or higher, but it can also be higher, but higher order phase transitions are very rare in the literature. The 2dxy model is an exception. Now, if in the vicinity of the critical temperature, the relevant physics takes place at distances much larger than the lattice spacing, and then all the short distance details don't matter anymore. This property is called universality, and all the models which have the same properties inside this vicinity of the second order phase transition are then one universality class. So to start with, we could write down a lot of models, but actually there are not so many different models, so that a lot of them drop into the same universality class, and then they are not really different in the limit. And now what does it mean to be in the same universality class? For instance, the critical temperature itself can well be different. Okay, sure, if you take two crystals with a different spacing between the points, then obviously the critical temperature will be different. That's not a criterion to refer to, but something which should be equal for all models in the same universality class is called the critical exponents. There is a set of them, about 10 all in all, but I will only illustrate this with one example. This exponent is unfortunately also called beta in the literature, so I'm using beta now for different things, but I have no choice because the literature is like that. We look at the magnetization. The magnetization, if temperature is 0, there will be a strong magnetization. If temperature increases, it will go down somehow, and at the critical temperature, then it will vanish. So this is what we call an autoparameter, something which is non-zero below the critical temperature and 0 above the critical temperature. And now if we are here next to the critical temperature, it will vanish somehow with this, in this form, and that the leading term will be proportional to Pc minus T to some power, and this power here is then the critical exponent beta. So if we go close enough, there will always be one power that dominates, so we can always single out this beta. If this is a typical critical exponent, and if all critical exponents coincide, then we have the full characteristics of a universality class. And of course, we can see beta is a good candidate for being universal for the simple reason that it is dimensionless. Yeah? For every exponent must be dimensionless in physics. So that's why it is a good quantity for being universal, unlike, for instance, the critical temperature itself. So this, how it goes here, in which slope it approaches 0, this can be the universal property. Good. So now the success of the Ising model, which seems an oversimplification of a spin model, is actually because one finds a lot of other models which are in the same class, and also a lot of materials, let's say solid state physics, which really behave in this way because they have really the same critical exponents in particular. So that is why the Ising model is so incredibly successful. And okay, other models which seem more sophisticated have actually less applications, so let us discuss a little bit the Ising model before proceeding then to field theory. The one-dimensional case was, this is what Ernst Ising did in his PhD thesis in 1925, suggested by his advisor, and his conclusion was that here the critical temperature is 0, or some people would say there is no critical temperature, but okay, it's a matter of terminology. But in any case, people agree that there should, to make the model interesting, there should be a finite critical temperature. Then you have a transition, you can discuss the transition and the critical exponents and so on. And so he concluded that the model is not really of interest, it's an oversimplification. And then during the war he was arrested, and he was not aware that in the meantime other people reconsidered this, and so well this is correct, but only in one dimension, but in higher dimensions than one, the critical temperature is finite, and the model is very well of interest. In particular, Piles in 41 gave an intuitive argument, which I will illustrate in a moment, and find it also in the textbook of Polyakov. And then a little later on, Sager gave a complete mathematical solution of it that is too complicated to revise here. But then the finite critical temperature can already be understood why there is such a difference between 1 and 2 dimensions. This can be understood based on the argument by Piles. In 3 dimensions, up to now, there is still no analytic solutions. So this is one of the great outstanding challenges. If somebody wants to become famous, this is a way to become famous. If somebody solves the 3D Ising model analytically, like Gonzaga did in 2 dimensions, it is not easy. Many people have tried. Also, Polyakov made a suggestions once, but it didn't work out. For practical reasons, it's not so important. It is solved to 7 digits numerically. Everything is known, but it would still be an intellectual challenge to have a precise analytical solution also in 3 dimensions or even higher dimensions. Now let us see why the one-dimensional spin model, let's say, have J positive, so a ferromagnetic spin model, no external magnetic field, why the critical temperature must be at 0. You can say we start from the uniform configuration, which has the highest probability, let's say, the lowest energy. And if we introduce one such a kink that it changes from positive to negative, this costs some extra energy, which is 2J over K, because this changes from 1 to -1, so that's why the 2, J over K, these are the coefficients. So the probability in each transition here, between each neighbors to have such a kink is this exponential. Now, of course, if we make the spin chain infinitely long, we will have such kinks, even an infinite number of them, even if the temperature is very low. So, and if you have such kinks, then the configuration is automatically symmetric between up and down, and we do not have a magnetization. So that means the only way out where we really have magnetization is the temperature is exactly 0, so this probability is 0 in each transition, and that means the critical temperature is at 0. So this already, for these 3 lines, actually reviewing the result of Ising's PhD thesis. Of course, he did this with a different technique, but we can see why the result must be like this in this short presentation. But then moreover, it also shows us what is the difference in 2 dimensions, and this is now Piles' argument. He says, well, basically you can start from the same situation. You start with a sea of spins, all with the same orientation, let's say all up. And now if you want to insert one which has the opposite orientation, well, it has 4 neighbors, so that the probability for this to happen is e to the -4 times J over T. So for small t, this will be suppressed, and then you can say, well, if you have a sea of 100,000 spins, then maybe 10 or 20 are expected to be opposite, but this is not so bad. You still have a magnetization. It is not completely saturated anymore, but the magnetization is still non-zero. And so that means if you have a few opposite spins, that doesn't symmetrize the situation, and this is different from 1 dimension. Now let us see what it takes to symmetrize the situation still. If they say we have an L times L lattice, so okay, a large system like L times L. L is something large, let's say 1000. Most spins, let's say, are parallel in some region, but we want to symmetrize the system. Then let's say we take a boundary, and on one side they are all up, and on the other side they are all down. So we would need a boundary that goes across, and so we need a boundary of which has roughly a boundary which has roughly length L also. And okay, it doesn't need, it can also be a large island going around here, but it's always the same. It needs to be of length of order L, more or less, the boundary, and then usually it has two neighbors connecting on both sides of the boundaries, so it is something like e to the minus 2jl for the number of spins involved, t, which suppresses this boundary. And again we can say, well, if we make L very large, then this will go to 0. So there will be no boundaries at final temperature. Yes, but there are a lot of possible boundaries. So the number of possible boundaries is also increasing if we make the system larger. And the mathematicians, these are now smart mathematicians of the 19th century, calculated that the number of possible loops or boundaries of a length L grows exponentially with L. This is a coefficient which is a constant which is known, but we do not need it for this argument. We just write a constant here. So there is a competition. On one side, if I increase L, this suppression is getting stronger, but on the other hand, there are also more possibilities. So we have a competition in the same weight class, let's say. So we can write this into one exponential, separate the L, and say that this is the amplification, L times this constant. And this is the suppression term given here. And now we can distinguish the two signs of this term into the round bracket. This changes the sign at this temperature, which is the critical temperature, and we see that this is in fact finite. So if T is below the critical temperature, then that means that this term will be the large L, this will be will be negative, large L will erase the boundaries, and there is a spontaneous magnetization, so the system will magnetize up to this temperature, and if it is larger, then making the system larger, more and more boundaries appear, and there will be boundaries all over the place of this length, and then there is no. Then the symmetry is restored, it cannot magnetize anymore. So the message is just that here, this is not 0 anymore, we have a phase below a critical temperature where the system is magnetized, and spontaneously, the symmetry of C2 symmetry is spontaneously broken up there, above the critical temperature. This is not the case anymore. And now we come to a dictionary which translates what we did last time into what we did now in the first part of today. So we started last time, we had the Euclidean time lattice. Now we were dealing with a d-dimensional space lattice. Later we will put both together, then we have quantum field theory. This time lattice was split into elementary time steps, and now we call this a crystal lattice spacing. Particle position was then given in each discrete time, we had a coordinate for that, and that would now correspond to the classical spin variables in each space point. A particle path, a discrete path, let's say, was then characterized by these positions in each time step, and if you take all these spin orientations together, this gives the spin configuration. And if we take the path integral over all paths, this corresponds to the functional integral here over all spin configurations. The Euclidean action that we introduced has a similar meaning as the Hamilton function here, and this was then divided by h bar, the Planck constant, which is similar to the temperature. Mathematically it plays the same role, just physically the temperature can be varied, but h bar not. If this is getting small, then the system is getting classical. Here we get some zero temperature physics. If we switch it on, we have quantum fluctuations, or here we call it thermal fluctuations, and again classical limit corresponds to 0 temperature. Here we have a kinetic energy term, so given by this nearest neighbor sites. And if we carry this out and say, well, the absolute value of such an x square is fixed, then it corresponds exactly to this coupling term that we have for the spin models. And then we can say here we said the continuum limit must be a to 0, which would then correspond to, okay, here I should still divide by the temperature to 0, but we saw that this was of course only one dimension. In higher dimensions, the continuum limit can also be at finite temperature. This is now a difference. Then here we have the potential energy term. This is a specific case of that would be an external magnetic field. We have the weight of each path, which is now called a Boltzmann factor, and a 1-point function, which corresponds to a magnetization, a 2-point function to a correlation function. The energy gap is the inverse correlation length, and the continuum limit is then the critical behavior. Okay, we say these terms here are a bit more general. These are kind of examples for them. But for the very important is the last line, and basically we only have to look at the ratio of psi over A. If this diverges, then we have something which we can call a continuum limit or a second order phase transition. So that's why we are actually always, if we do quantum field theory in the lattice, we are interested in second order phase transitions where psi over A diverges, or the vicinity of a second order phase transition. Usually we cannot simulate directly there or close to it for theoretical reasons, for practical reasons, but then we have to extrapolate to this point. Okay, now there are no comments so far. We get to field theory. Field theory considers a generalization of point mechanics to an infinite number of degrees of freedom. It can be on the classical or on the quantum level. And that means some small number that I call n in each space point. The time point doesn't count here because that we would have in the mechanics as well. So we have now space and time coordinates that are treated now on more equal footing. We have Minkowski space up to the signature, but this is actually the idea of relativity. It is not. Does not seem very realistic to have the coordinate as a function of time. We should treat space and time coordinate as something similar. And so if we do that, then we should deal with, we call this a space-time point, the x, which includes t and the space coordinate x. And then we don't have this as a function of t anymore, so we need to introduce something new on top of it, and this is what I call a field. The field is simply then a function, an abstract function of space-time point which fills the entire volume in space-time that we are considering. These are now the fields in the formulation of functional integral formulation. These are simply a function, and the function can be real, complex, and so on. We will look at examples. In this formulation, this is not an operator. In the canonical formulation, these are operator values, these fields are operated values. This has a lot of, makes things in many senses more tedious to deal with, but it has at least one notable advantage, that the notion of particles is more clear. Then we can say, well, in each space-time point we have excitations levels which correspond to the number of particles and so on. In our formulation here that we deal with, what is really a particle is not so obvious. So we have the situation that we deal in the language, in the formulas with fields, and in the language with particles, and in many books it is never really explained how they are related. They are related, it can be done, and for instance Wilczek has written articles where he introduces bifocals, some small excitations of the field around the ground configuration, but it's not so obvious. In any case, we introduce these fields as function of space-time points, and now we can distinguish what kind of fields we have. The simplest is where the field is a real number that we call a neutral scalar field. So this could be in this hole during 1 hour in each point the temperature or the pressure. That would be a neutral scalar field. Neutral because because to distinguish it from n equal 2, which is where Ci can be complex, Then we have a complex phase which can couple to a gauge field, and that's why we call this a charged scalar field, and to distinguish it from that, this one is then a neutral which cannot couple to a gauge field. So, this would be the case n equal 2. And then we can also build a doublet of two such complex components, so that psi is then in C2, and this is already the Higgs field, right? And initially, one would to start with, this has n4 components, n4 degrees of freedom in each space point. But we know, okay, without going in details, we know that there is actually only one left in nature or physical, which is n equal 1. This reduction is due to the Higgs mechanism. I will come back to that in a moment without going through the mechanism in detail. Now we can also introduce, put here a vector field, a vector in the relativistic sense here, which has these 4 components. That would be an abelian vector field, which describes the electromagnetic potential. Again, it has apparently 4 degrees of freedom in each point, but we know that there are here copies which are not really independent, which are related by gauge transformations. If we subtract them, we are left again with only n equal 2. And this 2 corresponds to the 2 polarization states of a photon. Okay, now on this vector level, we can also add an additional index and say these are now generators of some Lie groups. If we take in each direction, we have something which is not only a scalar, but the elements, the independent elements of the algebra are Lie groups. So the generators. So if this is SU3, we would have 8 of such generators. So then this is a gluon field. Strong interaction, and then we have, like the photon, 2 times 2 degrees of freedom after subtracting the gauge invariant copies, times 8, this number here, so n would be 16 in this case. Now a bit more tricky is the case of the weak gauge bosons. So first of all, we deal with SU2, so we have 3 generators, and then one would say, well, we have 2 times 3, 6 degrees of freedom. However, these gauge fields, as we know, are massive, and in massive field we have 3 polarization states, so it's not only 3 times 2, but it is actually 3 times 3, which makes 9 degrees of freedom in each space point. So we have 3 more than expected, and these 3 are exactly the 3 which are taken away from the Higgs field. So the number of degrees of freedom, just to illustrate, the number of degrees of freedom is conserved under the Higgs mechanism. So these are just to show the examples that exist. Now to work something out of that is that first we repeat this comparison. What was before the time is now space-time, and what was before the function of time is now the field as a function of space-time. And now we have to introduce this Lagrange function of the positions and velocities before. If we introduce something similar of the fields, we also need something which is defined in 4 dimensions, so we need a Lagrangian density, or I call it simply the Lagrangian in 4 dimensions, such a function here where one does not integrate only over time, but one integrates over some volume in space-time to get again the action. The action has a functional of the configuration of the field, where the field chooses its orientation in each space-time point. And a simple example would be given here. This is now known as the lambda 5-4 model. This is now a kinetic term. It has not only derivatives with time, but in all 4 directions. Then it follows a polynomial in the fields, which we will interpret in a moment. And here we have already introduced a notation where I call c the speed of light 1. And if we build such a Lagrangian from covariant building blocks, we get automatically a relativistic theory. This is without any steps in between, without any philosophy. There is actually a loophole. It could still be that the action is relativistic, is covariant, but it breaks spontaneously. And there is a whole industry of people in Indiana, Kostenecki et al., who wrote hundreds of papers about this scenario and introduced possible parameters for this breaking, which have all been verified now experimentally, and If we factor out the Planck scale, then the lower limit for the upper limit for each one is about 10 to the minus 27. So this scenario is really not so attractive anymore. So we can safely say that this is relativistic and the Lorentz invariance is there to stay. Also, without the scenario of a possible spontaneous symmetry breaking. So if we use relativistic terms in the Lagrangian, we have now automatically a relativistic theory, special relativistic. Now on the classical level, we would again insert this condition that the variation of the action is zero, which gives us the equations of motion for a field now out of coordinates of a particle. And mathematically, this is again this least action principle. So we would vary both the fields and the derivative of the fields. So this plus this term at fixed boundaries in 4D spacetime. So we can again, as we did last time, take here a partial derivative. So then move this derivative down here, change the sign, and then we have isolated the variation of the field. And we see if this must be zero for any variation, then this square bracket here must be zero. And here we have a condition for the field, which is then called the field equations, or the motion of the field equations. If we apply this, for instance, to this lambda phi to the 4 model, we see here we get this, this is the D'Alembert operator of the field, and here we simply get the derivative of the potential. Potential does not have the width, it's only of the fields without their derivatives, so that would be then the equation of motion of such a lambda phi to the 4 model. The place in classical field theory displays the role of Newton's equation. This is now the infinitesimal equation of motion. So if we have fixed boundary conditions, then in principle this phi of x and t could be evaluated, computed everywhere and at any time. So then the field values are determined everywhere up to some subtle mathematical exceptions. Now let us look at the even simpler case lambda to 0, which is called the free scalar field. Then we have this D'Alembert operator plus m square, phi is 0, it's known as the Klein-Borden equation. And if we interpret this in the sense of relativistic quantum mechanics, so this means energy square minus energy square plus 3 momentum square plus m square is 0, so we see now that it makes sense to call this parameter m. At least in this case it will replace the role of the particle mass. Another example is electrodynamics. Then the Lagrangian would have this form. This is the field strength tensor, which is gauge invariant. And the equations of motions, we don't have this this term here. We don't have at all, because all terms involve derivative. And if we evaluate this term, we are left with this equation, and these are the inhomogeneous Maxwell equations. Inhomogeneous because in general one could add here a source term, and then this would be equal to some source J, and then you see that this source is conserved. But and if we transform it into vector notation, this is what it looks like. And then you could say, well, there are still 2 other Maxwell equations left, which are known as the homogeneous ones. If we use vector potentials, the others 2 are implemented automatically. So that, for instance, if the divergence of B is 0 is automatically implemented if we use potentials. So with this ansatz, we have the full set of Maxwell equations. We have the whole classical electrodynamics included here. Now this takes us to another dictionary from point mechanics where we had the time. We now move to classical field theory where we deal with points in space-time. If we have particle coordinates, we now deal with fields. If we had a path, now we deal with field configurations in each time, in each space-time point. What was before a Lagrange function is now, I call this the Lagrangian. A few people also call that Lagrangian. There's a bit confusion, but I will consistently, in agreement with the majority of the literature, call this density here the Lagrangian. And then the action here is the integral over time, and here the integral over space-time. Imposing the variation of S to be 0, we get the equations of motions, and here the field equations, which correspond here to Newton's equation, and here in this case to a scalar field equation. This is a kinetic term, and this is the density of kinetic energy. Note that the mass is not included here because it's relativistic, and it has to enter in the potential in the mass term here, which would then be called here in that context would be called the harmonic oscillator potential. And then we got the next obvious term to be added would be a non-harmonic term, and here we will call it a quartic self-interaction. So this again we have the full analogy, and now we have established this relation, and this is all that we need to get now to quantum field theory. So this is the picture that we had in the very beginning, that we moved from classical mechanics to quantum mechanics by including not only one path but all paths. Now we have generalized this to classical field theory by considering not only trajectories but configurations of fields. And now we do the analogous steps. For delta S0 we single out one particular configuration, and if we include instead all configurations, then we get a formulation of quantum field theory. So now we're doing this last step, and basically it's not much left to do because we did all the preparations already. Now we get to a convenient formulation of quantum field theory. Just have to repeat what we did before. We considered this before as independent generalizations. Now we put them together and we get quantum field theory in the functional integral form, where a field here is now where we consider the sum over all configurations of a field. So we have now natural units h bar and c as 1, and then this the partition function would again be written as we have given before in Minkowski space. So the sum or the functional integral over all configurations, e to the I, the h bar is dropped because it's 1 times the action in Minkowski space. This is what we had last time, and we also saw last time that the convergence behavior of this term is much better if we move to Euclidean space, so if we deal with imaginary time. And in particular we have a minus here, not this I anymore. We have an Euclidean action where kinetic and potential energy are additive, and so we see the minimum action here. We see this very explicitly as the strongest contribution, and the rest is suppressed exponentially, just as we have seen for the spin models before. So then now this means a functional integral over all configurations. That means in each space-time point over all we integrate over all values that the field can take. So this is a huge set of integrals, so that's still what we have to deal with. This is of course a divergence expression, but if we want to evaluate expectation values, we divide two expressions of this type by one by the other one, and then we can get something finite. So again, this functional measure here symbolizes in each point an integral, let's say for a real scalar field, an integral from -infinity to infinite over the field values. So this is a huge set of integrals. And we saw in the quantum mechanics formulation what we can do to make it finite. We regularized the time by some discrete time steps. Now, of course, we have to do the same with space-time and introduce instead space-time, discrete space-time points, and this is again this lattice structure that we had, okay, say with some spacing A. Now we have an integral over each lattice point, so at least mathematically the system is then well defined. To carry out this integral is still a major issue, but at least we have some well-defined term to start with if we do this lattice regularization. So then the expectation value of some observable of interest would be that we have here the product of our lattice points, and each point the integral over the field values in this site, and then here the observable as a function of the field configuration with the exponential suppression normalized by the partition function, and the same on the lattice structure as well, of course. And then in the continuum limit both will go to infinity, but the ratio here can well be finite. So this can be viewed as a merger of Euclidean quantum mechanics and time lattice and spin models. So here we have discretized time and here we have discretized space. If we put both together, we have quantum field theory. This is it seems very simple, but it is actually the only regularization which captures finite couplings in the interaction, so which does not depend on perturbative expansion. So for instance, if you have this lambda phi to the 4th term, similar as the anharmonic oscillator last time, we can deal with lambda 1 or even larger principle. The formulation always works, and we can evaluate such formulations at least numerically. So it is most popular to have a hypercubic lattice, so in all 4 directions, let's say a cubic structure with spacing 1. So the sides here are integers time in each direction times some spacing a. And then we still have to see how to formulate the action or the Lagrangian on the lattice. This is not completely obvious because we have used derivatives, and in the discrete structure actually derivatives do not exist. So the simplest case here for lambda phi to the 4 model is that we would take differences of nearest neighbors. So that would be the obvious thing to do. So we replace delta mu of phi by phi of x plus a times mu. U is a unit vector in mu direction minus phi of x, and divide this by a. This is of course the simplest way to do it. It's not the only way. We could also do it more complicated and introduce coupling to more distant spacings. But again, it doesn't matter. Again, here we have this powerful property of universality, which says in the continuum limit of observables, this will all agree. If we would not have this powerful property, then we would have a complete mess in this regularization. Then if we say we do this differently, this discretization, we get a different result each time, then we would have a disaster. We don't know what to trust and what could make sense physically. But thanks to this property, which holds in field theory, not in quantum mechanics, but in field theory, universality tells us that different regularizations of this type can have different practical benefits or advantages or disadvantages in the simulation, but in the continuum limits they will always lead to the same results. Thanks to universality, we can trust one of these formulations. Theoretically, the condition is that the couplings between the neighbors here must drop off at least exponentially. This is the condition. Then we can, if here in these cases, of course, we stop at a finite distance, then we don't have a problem. Then we can trust that in the continuum limit we recover the same result for each formulation. And for a non-perturbative observable, this is actually the best definition that we can give. Discretize it in this way, take the continuum limit, and that is the result. Unfortunately, we don't have continuum results to compare with. We can only, if it's a model that describes phenomenology like UCD, then we can only compare with the phenomenological, the experimental results measured on hadrons. So this is a kind of discrete derivative, and then we have a formulation which can again be treated by Monte Carlo simulations, as is sketched last time. We do the same as before. We interpret this ratio here, e to the minus s, with this normalization, as the probability for one field configuration given here, and then we tell the computer to perform a Monte Carlo simulations. That means to generate a lot of random configurations which are distributed with this probability distribution. So those with lower actions have higher probability and so on, and then we let it terminalize. We start with some configuration and obey detailed balance until it is terminalized, as we have seen last time, and then we have to decorrelate to separate them long enough in the simulation so that they are independent and correct in this sense the good configurations. And if we have, let's say, 10,000 of them, we can perform a numerical measurement of them. So this is then an approximation for a functional integral used to measure observables. Then we have necessarily statistical errors because the set of configurations is finite, systematic errors because we have to simulate a finite lattice spacing, finite volume, and sometimes also other parameters have to be extrapolated to the values that we like because we cannot simulate directly there for some technical reasons, like the biomass. But in principle, this is nevertheless straightforward, and up to some uncertainty we have safe results. There can be a problem, however. The problem is that this ansatz, this interpretation as a probability fails if the Euclidean action is not really positive anymore. For the examples that we have seen, and that most examples of interest, it is really positive. But there are counterexamples. For instance, if we introduce such a theta term in a theory Q which has topological sectors. So this is a topological sector where topological charge, which this is integer, which depends on the deep field configuration. And in some sense, for instance, in QCD has such sectors, and if we write it as a general ansatz with all terms allowed by powers, then it would be natural to add such a term. And then the Euclidean action is not really positive anymore. And this trick that the I disappears does not fully work anymore, then we have a problem. And okay, by the way, this theta seems to be less than 10 to the minus 10 in nature. We do not really understand why. It's known as the Song CP problem, but simulating that is a real problem. And the more realistic case is simulating finite baryon density, where one introduces a chemical potential. So this is only relevant for states of very high energy, like neutron stars, but this is something which cannot be done here immediately. So it can, sometimes people say it cannot be done at all. This is a bit wrong, because we can of course simulate by, for instance, dropping the imaginary part in the simulation and then take your configurations and reweight them with a complex phase. This is not wrong, this is in principle correct, but then we have again the situation that we described last time, that there is a lot of cancellations going on. So maybe you have 10,000 configurations, but then we notice that most of them cancel each other, and at the end you're left with something which corresponds to a very huge error bar, statistical error bars. And technically speaking, it means that if you want to measure something with stable errors, the quest of statistics, the requirement of statistics grows exponentially in the volume. This is something very bad, because okay, then you can maybe do it in a very small system, but if you want to make it larger, then you get the errors get out of control. This is known as the sign problem. Maybe one should rather call it complex phase problem, but this is the term in the literature. And this is essentially unsolved. So it's possible that somebody finds a magic algorithm which overcomes this problem. And in some toy models this is achieved, but not in these examples of QCD, still not. And this is why our knowledge of the QCD phase diagram is still incomplete. So what we know is, okay, here we have temperature axis and chemical potential axis. So this we know very well. We know where is this chiral crossover is around 160 MeV, and then we suppose here it goes down, speculations about triple points and all kind of new phases, but unless at very small mu these techniques work, but from here on, well, actually the results are quite uncertain, and there is no other technique than the lattice which would really clarify that. So just to mention, this interpretation here requires this assumption, and if this doesn't hold, then we have a serious problem. But let us assume now that this holds, and I look now at the simple. Okay, I cannot do here live simulations, but I can work out a simple case which we can compute in full and show that all these technical concepts actually work in practice. And this is the free scalar field. It's a simple, instructive example, and we can solve it analytically. And it's basically all that we can do analytically because it corresponds to many harmonic oscillators. So that's why. So the functional integrals are all of Gaussian type, so that's why we can do it. So that would be the standard lattice regularization of the free scalar field. So this is the kinetic term here. I divide, let's say we could divide by a squared here, and then we have a to the d, where d is the dimension of space-time. So I put here a to the d minus 2 already, and then here we have this a squared here. It is a bit more convenient in this way, because then in this bracket everything is dimensionless. So this MA is dimensionless. Again, this mu is a unit vector in some direction mu. And we can certainly write this now in a matrix notation, say this is phi x, phi y, and some matrix in between. So which couples that this will be the diagonal elements, and here we also have some off-diagonal elements. And the lattice partition function is then this functional integral here with the integral over each of these phi x given in the Euclidean action. So this is the style. Again, this discretization is not unique, but for other ones we will, in the continuum limit, we will get the same result. Maybe I should anticipate, this will be the fourth lecture. I will discuss in particular chiral symmetry of fermions, and then this simple discretization, which seems obvious to do, actually fails. For the lattice Dirac operator, this is not applicable, and there we have to look for something more complicated and very refined to maintain chiral symmetry. Just to mention that this is not something which can always be done. But for scalar fields it works very well. And another point is that this matrix here can certainly be written in a symmetric form. So if we have off-diagonal elements, we can spread them above and below the diagonal, so we can assume M to be symmetric. And once we do this, okay, for instance, in one dimension we have then here the diagonal element of the mass term, and then the second derivative has this -1, which we spread symmetrically, and then this +2 inside here. This is just if we carry out the square here. So we have then the -2 from this, and -1 of the mixed terms here above and below. So this is, in higher dimensions we have a bit more complicated structure of the matrix. We have more off-diagonal elements, but it is still symmetric. And if we have a symmetric matrix, we know that we can diagonalize it with the help of an orthogonal matrix. So this is an orthogonal matrix, this is root symmetric. So if we do this base transformation, we know it will be diagonal. Call these diagonal elements dn, d1 to dn. And now we do the corresponding substitution. Phi prime is now omega times this phi. The Jacobian is 1 because this is orthogonal, so we don't need to worry about extra terms. And now we simply carry out these integrals one by one in the diagonal form, and then the integrals are completely independent. Straight Gauss integrals, we know that goes with the inverse square root of the diagonal elements with some extra factor here. And this product here is actually the determinant of this matrix D. And then, since it's related by a base transformation to M, it is also the determinant of the matrix M. So here we can compute this lattice partition function completely. But okay, again, the partition function is something that we need, but it is not the ultimate quantity of interest. What we really want are expectation values. So now let us address the expectation values, and in particular we look at this two-point function phi x, phi y, which is now given here. This term we know already, this is all in the lattice, and now we have to do the integral with these extra factors here. And here we introduce now a technique which is very useful, these source fields, similar to the magnetic, external magnetic field in the spin models, but now it is important that they are space-time dependent, so it can be different on each lattice side. I call this now Jx, the source field. This is actually, here it is a technical trick. I will put it to 0 at the end, but it is very useful for the intermediate steps. So first I generalize the partition function by the addition of such a source field, J times psi, where this means that we sum over this in each space-time point, and this is a shorthand notation. This is phi x, m, x, y, phi y, but don't write the indices now for convenience. And this generalization of the partition function is known as the generating function. Now this expectation value of phi x times phi y is now obviously obtained if we take these functional derivatives with respect to j here in x and in y, and then we still divide by c, and then after taking derivatives we put j to 0, and then we see that we have simply rewritten this in a convenient form. And the other, actually we were interested in this connected correlation function, where we subtract this disconnected piece here, which is the same because the space-time, no space-time term is different than another one. So we have to subtract this. And the trick is simply that we take the two functional derivatives here of the logarithm of c. This can be checked in a few lines of calculation, and moreover it even extends to 3, 4, 5-point functions, etc. And one of the exercises that I distributed is to check this explicitly for a 3-point function. This takes about maybe 2 pages of calculus, but it is straightforward. It's very nice to do it and see that. Okay, if we take the first derivative, we have this 1 over c, and then the phi, and then the second one here, we can then apply the derivative to the 1 over c, then we get this term here which is subtracted, and then we can also apply it to the prefactor, then we get exactly what is left here. So this is very elegant. We can always use that to get directly the connected correlation function. And okay, so now we can refer to this formulation. And now we complete the square and the exponent. So this is the standard trick that we always do if we have such a mixed exponent. We always want to get rid of this j of these mixed terms because they are unpractical to integrate. So we do a substitution here to complete the squares. So we have now this phi tilde and phi tilde square, and then this substitution kills this mixed term, and we are left with a j square term here. Obviously, okay, we can substitute this back here and we see that it is the same, and also Jacobian is 1 again, so we are not doing anything bad here. And we can now simply, okay, I think it's obvious now, if we plug this in here, then we get this plus j phi here, which cancels that one, and then the j square terms cancelled out, and we are left with exactly with this term here. And now we can perform the integral over the phi tilde, and this is, now j does not appear anymore, so we can simply insert the result that we had before. This is constant over square root of the determinant of m, and then we still have this term here. Now if we want to collect a 2-point function, so first of all we can use this formulation with the logarithm of c, and then we see this term does not contribute at all. Because okay, the logarithm splits this into 2 additive terms, and here j is not involved, so this does not appear at all. And if we now take the derivatives here 2 times and then put j to 0, it is easy to see that we are left with this n to the -1 at the components x and y, where the 2-point function is taken with 1/2, that 1/2 is up here, so this is the result in coordinate space. So we have an explicit result in coordinate space, but it's still, okay, we have this complicated matrix M, we can still not really make sense of it. To really make sense of it, we go now to momentum space. So the momentum space has the advantage that this M will be diagonal, and then we can interpret this result directly. So first of all, we perform now a Fourier transform in momentum space of the scalar field. This is how we put it in this is the scalar field in momentum space, and we integrate here over the Breuer zone. This is what one usually does also in solid state physics. So for a equals 0, this would then be the full integral, but for finite a, we have periodic copies over the Breuer zone, and this is then and a is up here, so this is the Fourier transform on a lattice. So just to illustrate this, if we have infinite volume and a continuous space, this is the situation that we are ultimately interested in. But if we go to a finite volume, then the momenta are discrete, or alternatively we can have discrete coordinates, then the momenta will be confined to a finite volume, which is the Breuer zone. And then the place where we really do the simulation is that we combine both, so we have a finite lattice where both P is discrete and confined to a Breuer zone. So this is the generic scope of the Fourier transforms, and we are interested now in this term phi x times phi x plus a times mu, which is also here somewhere. Okay, if we take the square, because we have to take the square in this, then the kinetic term, and this square here brings in everything else is diagonal. So this is the only tricky term to take is this product. And now we rewrite this product in momentum space. Then we have a phi k, phi p. Here this comes with an exponent e to the chi x and e to the different momentum p. And here we have to shift by this mu. And we integrate twice over the Bria zone with the prefactor squared. And the next step is that we actually need to the sum over all sides x of this term. So let's take this sum. Look at this term and separate the term, the only factor which contains x we write at the very end. So even this I pay a mu, this does not contain x, so let's anticipate that. So we only have this sum over x to be carried out, and we know that this is a discrete version of there's a periodic version of a delta function. This is known as the Poisson equation. And the lattice, if something is on the lattice, then in momentum space it must be periodic. So this is these are delta functions with 2 pi over a periodic copies. Actually, here it doesn't matter because we only inside the Bria zone, so it's like one delta function. So this is like the discrete version of, if this would be an integral, then it would be the continuous space delta function. Now it is discrete, so there are periodic delta functions. So we can apply this, put k to minus pi, then we have here k to minus pi, and we are left with this factor, and we have here where we have used this identity. And of course, we always assume here that the space volume is infinite, so we sum over the entire set of points here. Now insert this into the sum. This is now the action, the lattice action here. We have this sum over x to be done, and then here we have phi x, and this is just like the second derivative, like the Laplacian and the mass term. Now if we put it into momentum space, this is exactly then we can write this m of p in momentum space, and this is exactly the property that m of p is diagonal in momentum space. So what we can see here quite directly is this representation with a cosine. So here we have 2 times this minus these 2 mixed factors which go with the e to the plus minus the faces. This is 1 minus cosine, and now then there is an identity that this 1 minus cosine is actually okay. This corresponds to this p mu hat squared, where we take half the element. This is a trigonometric identity, can be checked within 2 lines if we write exponential terms. And here we have a very clear interpretation that this is kind of a lattice momentum, right? If we take a very small, then only the first term in the expansion of the sinus survives, and divided by this here, so we get then p mu. On the lattice we have then corrections, but in the continuum limit this will turn back to p mu. And now we know what m of p is. It is the lattice version of p squared times plus n squared. And what we have evaluated now is this 2-point function, which I write here in momentum space, phi of p minus p, and so it's the inverse of this n, is the inverse of this p squared plus n squared on the lattice, and in the continuum it turns into this term 1 over p squared plus n squared. Not a surprising result, but now we have computed it fully analytically. Now we still want to apply the technique to extract the energies, and exactly in the way that I described schematically before, but we want to make it now fully explicit. And we said we need a 2-point function with separation in Euclidean time, and we have to see how it decays in Euclidean time, and the coefficient of the decay gives us the energy. So let us do that. To do that, we first have to go back, at least in the time direction, we have to go back to coordinate space, otherwise we cannot achieve this separation. So let us transform only that coordinate back. So this is the inverse Fourier transform, actually the one before was the inverse. This is the Fourier transform in the Euclidean time direction. And we look at the 2-point function where one is at time 0 and the other one is at some time t, which is non-zero. And so now we have this term, we write the expectation value down here, and we have this extra exponential with the integral. The T0 does not contribute, so we have this one factor here to be integrated over P4 as given here. And this is a complex number on the unit circle, right? T is real and P4 is real. On the unit circle, call it C. And what we do here is that we perform some windings on this unit circle with this integral over P4. Now if we do the substitutions, we see that what we will get are the contributions of the singularity, the residuum of the singularity, which is encoded in here. So here we can have solutions inside and outside the circle, but only those inside the circle will contribute. And if we interpret this P4 as I times, okay, it's not written here, here it is written, I times P4 is minus the energy. So, so we see that only the positive energy, the condition that only the point inside the circle contributes means only the positive energy value contributes. So we need a solution of this term being 0. So we have a pole with the additional condition that the energy must be positive. Then we get the energies. And this, okay, this is again P is equal to I times pi 4. We need a solution of this equation. So I have replaced now P4 by I times E. So this turns into a sine hyperbolic. And we have the condition that E is positive. So E is now, we solve for that, is an arc sine hyperbolic by such a complicated term. This is the lattice solution, but clearly if you take now the limit a to 0, it simplifies to this square root, so this is exactly the relativistic energy that we expect. And we see very clearly why okay, here there could be two solutions with positive and negative energies, and we see here very clearly that only this describes the exponential decay, so only this is the physical solution. So in practice this means the continuum where I feel, let's say, only one momentum component, then in the continuum for mass 0 the energy would go like this. On the lattice it is deformed here to something which for small momentum is asymptotically the same as in the continuum, but for larger momentum it must necessarily be periodic in the Bria zone. Sorry for the quality of these plots, but I think you see what I mean to show. It must be periodic over the Bria zone, so at 2 pi over a it must be 0 again, so it corresponds to this picture. Now if we take a continuum limit a smaller and smaller, let's say at a fixed momentum, then we're getting closer and closer in this region, and we're getting better and better to the continuum result, we're getting the right result. Or we can do the same at a finite mass, then at 0 momentum we have here this energy which is simply the mass, and here in the continuum it raises like this, and the lattice it will raise asymptotically in the same way. So if our physical momentum is small compared to 2 pi over a, so let's say we have a fixed physical momentum and we make a very small, then this is enhanced and we are here in a place which is very close to the continuum curve, then we get the right result up to a very small correction. But of course we should not work with a momentum which is half of the edge of the Bria zone or getting close to the Bria zone, then we have a significant difference here, then we have lattice arc effects due to the higher terms in this expansion. So this is the situation that we have, and this is quite realistic also if we perform measurements. We perform measurements with such decays where we measure the decay of endpoint functions, and then we extrapolate them to the continuum, and this behavior is in fact very realistic to look at. Okay, so comments to this point. How are we with the time? I still have a small addition that can do in some 10 minutes, which I can do either now or next time. Are you still fit to go on with? Just mention because so far this is the course is dedicated to the lattice, and I presented so far everything as if the lattice was the only regularization. Of course this is not true. Just want to mention at this point that there are also continuum regularizations and show a little bit how they work. They apply very well to perturbation theory. Again, we have seen how perturbation theory works. We leave the quadratic term, which are the Gauss integrals in the exponent, and this term we cannot handle exactly, this continuum functional integral, so the rest you expand as a series. In this case, the next term would be lambda square term lambda, and then each time we have more integrals and more phi fields to contract to build these expectation values. And so we have the building block that we have to look at is always the expectation value of a product of two fields. And as we see here, it can often happen that they are at the same point. We have necessarily here higher powers than 2. This is what makes the interaction. So we have here fields to be contracted at the same point. And we have seen this expression already. We are now already in the continuum. So this is 1 over p squared plus n squared. And now we see that in more than 2 or more dimensions, this term is of course divergent. And then we need also in the continuum a regularization to evaluate this perturbative series. By the way, you can also do perturbation theory on the lattice, but it is not convenient for that. So a one-loop calculation on the lattice gives about as much work as a two-loop calculation in the continuum. So it is possible, but it is not practical. So for this purpose, the lattice is not especially good. So if you want to do perturbation theory, which is not the goal of this lecture, but if you want to do it, then I would rather recommend continuum regularizations. So the way to regularize this traditional way was suggested by Aula in the 50s, and it was also used, was the dominant method in the 60s. It said if you replace this term by subtracting a similar term where you plug in an artificial very large mass, the Pauli-Villars mass squared, then of course the integral to very large momentum is finite because you have this cancellation. You carry out all the calculation you want to do, and at the very end you take this Pauli-Villars mass to infinite. This looks actually like a very good concept. So for instance, it is clearly better than just putting here a momentum cutoff. That breaks all symmetries which are possible. This concept maintains, for instance, covariance, rotation, translation symmetry, and so on the regularized level. So it is quite a smart procedure, and it was also applied successfully to quantum electrodynamics, but when people wanted to introduce then the electroweak sector of the standard model, there it failed, and for some time people did not find the gauge invariant. It did not give something which was still gauge invariant on the regularized level, and once it is spoiled, then it will not return in the continuum, in the